Swayam Prabha. Digital India. Educated India.
Hello and welcome back once again. Okay, so right now we are talking about processing of metal matrix composites, and with regard to that we discussed two very important aspects of MMCs with regard to the reinforcement which is added to the composite material, that is the weighting of the particles with the metallic matrix, and secondly the distribution of the reinforcement particles. These two are very important because weighting of particles will decide whether there will be a good bonding or not, and distribution will decide whether you are going to get uniform properties or not. Uniform properties or improved properties in the composite material. Okay. So in the previous class we talked about this weighting aspect, which basically depends on the contact angle between the liquid and the solid reinforcement particles. You need a low enough contact angle for good weighting to happen. And then only you can expect a good bond to form between the particles and the matrix. And we have also discussed the process parameters which can affect this weighting, and we have seen temperature is one of the main parameters which affects the contact angle. That could be seen if you take an example of a particular system. For example, if you talk about this kind of aluminium silicon carbide composites, then with regard to the contact angle between silicon carbide and aluminium, you can plot the contact angle with respect to temperature and see at different temperatures how the contact angle varies with time. So let's say for the contact angle we are talking about a range from 45 to 135 degree. Okay, and then you see it with respect to the time as to how it varies with time at a particular temperature. So as you increase the time, the contact angle will decrease, and eventually at a particular time it will level off. Okay, so it will vary something like this. And what is the final contact angle? That is the contact angle when it is leveling off. That would depend on the temperature. So you would see that higher the temperature, lower will be the final contact angle. Okay. So like that, it can be shown for different temperatures. Let's say for these three curves, we have these three temperatures. So you can see higher the temperature, lower is the contact angle, and that can also be shown with another plot like this. If you plot the contact angle with respect to temperature, and see how the initial and the final angle varies with temperature. The initial angle is this one, and the final angle is the one after saturation. Okay. So here also you would see that as the temperature is increased, both the initial as well as the final contact angle will decrease. Right? So if you have a higher temperature during the processing, you can expect a better weighting to happen. So that is how you decide your process temperature when you talk about a particular composite system. Okay, so this was for this aluminum silicon carbide composite. The next important aspect, as I said before, is the distribution of particles. The reinforcement particles should be distributed uniformly, and it should be ensured that there is no agglomeration or clustering of particles. Okay. So whether the particles will be homogeneously distributed or will be agglomerated, that would depend on the solidification behavior of the composite material when you actually cool down the entire system after adding the particles into the molten metal. Okay. So let us talk about that as to what happens during that process of solidification when you have these particles suspended in the liquid metal. Okay. So you will have to see the interaction between the suspended particles and the metal. During solidification. And this interaction would depend on certain parameters, particularly the temperature field of the particle matrix system. So during solidification, the heat is extracted, so you have heat flow in a particular direction, and depending on this heat flow, you will have a temperature field for the particle matrix system. Around the particles, you will have a temperature field. Okay. So how this temperature field will vary, if you need to see that, you'll have to look at the isotherms, the temperature isotherms, especially the isotherms of the melting point of the matrix material. So when you extract the heat, the solid phase will form. So you will have a solidification front which grows around the liquid. And how this solidification front interacts with the particles will decide their distribution. Okay. So if the particles are pushed by this solidification front, then it will lead to clustering or agglomeration of particles. Whereas if the solidification front engulfs the particles, then it will lead to uniform distribution. And whether pushing or engulfing will happen, for that you need to look at the isotherms or the temperature field, as I said. And one of the material properties which will affect these isotherms is the thermal conductivity. Because here you have added a completely different material into the molten metal, and the thermal conductivity of that material, that reinforcement phase, is different from that of the metallic matrix, right? And therefore the temperature field will depend on the thermal conductivity of both of these materials. So you will have to actually look at the thermal conductivity ratio. Kp by Km, where Kp is the thermal conductivity of the particles, and Km is the thermal conductivity of the metal. So whether this ratio, if we call that as alpha, whether this is 1, less than 1 or more than 1, basis that the temperature field around the particles will change. In other words, the isotherms will depend on the value of alpha, whether it is equal to 1, less than 1 or more than 1. Okay. So let us see these three scenarios when it is equal to 1, less than 1 and greater than 1. Okay. So the temperature distribution is a function of the thermal conductivity ratio. And for alpha equal to 1, the heat flux lines lie along the heat flow direction. Which is basically the z direction. We define z direction as this vertical direction, and x is the horizontal direction in this particle matrix system that we are talking about. Okay. So the heat flux lines are along the z direction, and the isotherms are in a direction which is perpendicular to this heat flow lines. Okay. So isotherms therefore will be in the x direction. So this is a scenario when alpha is equal to 1, the heat flux lines are along the z direction and the isotherms lie along the x direction. Okay. So isotherms are parallel to the x direction when alpha is equal to 1. Now if alpha deviates from 1, if it is more than or less than 1, then these isotherms will also be deflected close to the particles. So when alpha differs from 1, the isotherms are deflected in the vicinity of the particles. What I mean to say by that can be understood from these diagrams. So let's say this is a particle and these are the isotherm lines. Okay. So this is the scenario when alpha is equal to 1. Now let us see when alpha is less than 1 and greater than 1, how does this isotherm change, especially near the particles. Okay. So for a scenario when alpha is less than 1, that is when particles have lower thermal conductivity compared to the metal, then the isotherms will be deflated near the particle and will diverge away from the particles. right? So this is how it will be, how the isotherms will behave when alpha is less than 1. Okay. The isotherms will be deflected in the vicinity of the particles and will be diverging away from the particle. And when it is greater than 1, then it will be the opposite scenario. The isotherms will converge toward the particle. Right? So this is the scenario when alpha is greater than 1. The isotherms converge towards the particle. Okay. Now, we were talking about the solidification front or the solid liquid interface and its interaction with the particle. Okay. So that is what is going to decide the distribution of the particles, whether they will be clustered or uniformly distributed, or in other words, whether they will be pushed by this interface or will be engulfed. So the solid liquid interface follows the isotherms of the melting point. So it is assumed that the solid liquid interface follows the isotherm for the melting point of the matrix material. And therefore, the dependence of this interface on alpha with respect to the particle will be also similar to how the temperature isotherms behave when the alpha is changed from 1 to either less than 1 or more than 1. Okay. So the pattern of variation of the isotherms with respect to alpha will be same as the variation of the solid liquid interface with respect to alpha. Okay. So that means for alpha equal to 1, the interface will be planar. For alpha less than 1, it was diverging away from the particles, so it will form a bump. And for alpha greater than 1, the interface will form a trough near the particle. Right, so this is for a scenario where the thermal conductivity of the particles is lower than that of the matrix, and this is for a scenario when the thermal conductivity of the particles is higher than the matrix. So for this scenario, you can easily realize now that if this happens, the particles will roll down along this bump and the interface will push the particles. So alpha less than 1 will lead to pushing of particles, whereas here you have a trough developed near the particles. So this is going to lead to engulfment of particles. Engulfing is conducive for homogeneous distribution of the particles in the solidified composite, whereas pushing leads to clustering or agglomeration of particles. Right, so this is how the variation of the temperature field with respect to alpha will affect the interaction of the solid liquid interface with the particles, and that in turn will decide whether the particles will be pushed leading to clustering or engulfed leading to uniform distribution. Okay, so clustering means particles will be clustered or segregated along the interdendritic region, whereas engulfing leads to uniform distribution inside the grains. Okay, so let me show you how the particle distributions look like and what is their effect on the composite properties. So these are some micrographs taken from this aluminium, lithium, silicon carbide composites. Okay, so here the matrix material is an aluminium lithium alloy and the reinforcement is silicon carbide particles, as you could see from here. Okay, so these are the particles, the black colored particles that you see over here. Those are the silicon carbide particles, and the rest is the aluminium matrix. Okay, so this is a uniform distribution of particles where you can see the individual particles in the microstructure, right? So this is what we expect in a good composite, and when you have a distribution like this, then only you can expect improved properties in a composite material. Okay, on the other hand, when the particles are agglomerated or clustered, you will see a microstructure like this one. Okay, the second micrograph on top that you see. Okay, so here you can see you cannot really distinguish the individual particles, rather you see an agglomerate of particles, right? So this kind of distribution of particles is not at all desirable in a composite material because this is going to deteriorate the properties. For example, on this micrograph, you can see a crack which has nucleated near the particle cluster. Okay, so these particle clusters can serve as stress concentration sites, and the crack can nucleate easily along those sites, and that will lead to an early fracture, and therefore the strength and the ductility of the material will be adversely affected, right? So that is why, as I said before, it is always recommended to avoid clustering or agglomeration of particles, and you should have a composite where the distribution is like this, where the particles are uniformly distributed across the matrix material. The particle clusters can also get associated with the porosity. So here you can see an association of particle cluster and a pore, and this is again not good for the composite because this kind of sites also can act as the crack nucleation site and lead to early fracture. Okay. So the point to take home here is that you should have a composite material in which the reinforcement phase should be homogeneously distributed for having good properties or improved properties in the material. Okay. With that, we come to the end of this lecture. Thank you for your attention.